Good morning, honors chemistry students. The last of the problems that I would like to do for you in this particular assignment is problem 16, which reads, the insecticide DDT has the following composition by mass: 47.5% carbon, 2.5% hydrogen, and 50.0% chlorine. Determine the empirical formula of the compound. So this is a fairly straightforward, typical honors chemistry problem in which you're given percent composition of a compound like DDT, which is an insecticide that's used to kill all sorts of pests. You're given the percent composition of that compound: 47.5% carbon, 22.54% hydrogen, and 50.0% chlorine. And you're asked to determine the empirical formula of that compound. In thinking about this, we step towards the known, unknown solution style of problem solving to solve this problem. What you're being asked to find in the last statement is the empirical formula of this compound. In other words, you're being asked to find the ratio of carbon to hydrogen to chlorine in the compound. You don't know what that mole ratio is, but that's what you're seeking to determine. You're given percent composition data. In other words, you're told that the percent of carbon in the compound is 47.5%, and you're told the percent hydrogen in the compound is 2.54%, and you're told the percent of chlorine in the compound is 50.00% chlorine. Now, it stands to reason that if you totaled these percentages, they should come close to 100. And in fact, as I total these, the percentage comes to 100.4%. I wouldn't let that bother me, but it should be close to 100%. That being said, when you think of your solution pathway, this is a time-honored standard solution pathway for such a problem. And it goes something like this. You're given percent composition, and you convert percent composition to mass because you assume that percent composition is mass, and you convert mass to moles of an atom because all roads go down the mole road. To go from mass to moles of a given individual atom, you're going to use gram atomic mass. And to go from moles to a mole ratio, you divide by the smallest number of moles and you multiply by some number until you get a whole number. So the way the solution pathway goes is percent to mass, mass to mole, divide by small, multiply by whole. So that's the general approach that we use. So if you say that over and over and over, percent to mass, mass to mole, divide by small, multiply to a whole, you'll remember that, and you can tackle any of these types of percent composition problems. So the first thing you're going to do is to set off to calculate the moles of each of these substances. To do that, we're going to assume that percent composition represents mass, because if we had 100 grams of this compound, 47.5 grams would be carbon, 2.54 grams would be hydrogen, and 50.00 grams would be chlorine. To convert from mass to moles, you're going to need to know the gram atomic mass of each substance. So the gram atomic mass of carbon off the periodic table is 12.011 grams of carbon per mole. The gram atomic mass of hydrogen is 1.00795 grams of hydrogen per mole of hydrogen. And the percent composition of chlorine, the gram atomic mass of chlorine is in fact 35.453 grams of chlorine per mole of chlorine. And you can get those values straight off the periodic table. That being said, the first objective is to calculate the moles of individual atoms that you have in the compound. So in other words, you're going to calculate the moles of carbon in some units of MOL of carbon, and you're going to do that by assuming 47.5% is 47.5 grams of carbon. And you're going to convert grams of carbon to moles of carbon using the gram atomic mass, because you know that 1 mole of carbon atoms has a mass of 12.011 grams of carbon. Grams of carbon cancel, and you get a value of 3.95 moles of carbon. And again, you should have the same level of precision in your answer as you do in the least precise measurement. 47.5 has 3 decimal places. You draw an arrow from the Pacific till you get to the first non-zero digit. Every digit thereafter is significant. So 47.5 has 3 sig figs, 3.95 has 3 as well, so you're good. You turn your attention to calculating the moles of hydrogen. And again, 2.54%, you assume that represents mass. And you convert to moles using the gram atomic mass. Keep in mind that the gram atomic mass is always the bridge between mass to moles. So you know that 1 mole of hydrogen has a mass of 1.00795 grams of hydrogen. That product turns out to be 2.52, once you round it, moles of hydrogen. Then you turn your attention to the moles of chlorine. So moles of chlorine are found in some units of MOL of chlorine. Again, 50.00% represents 50.00 grams. It's quite a trick, isn't it? And you know that each mole of chlorine has a mass of 35.453 grams of chlorine. Grams cancels out, and you're left with moles of chlorine. And in this case, you come up with 1.41 moles of chlorine. It's clear that you have more than a mole of chlorine because the mass that you have available is twice the mass, not twice the mass, but greater than the gram atomic mass. The same can be said for hydrogen, and the same can be said for carbon. So that being said, we've assumed that percent is mass. We converted mass to moles using the gram atomic mass. Now we're going to divide by the smallest number of moles. And in examining your products, the smallest number of moles is that for chlorine. So we're going to divide each of these answers by 1.41 moles of chlorine. The units are going to cancel, and you get a value here of 2.80, a value here of 1.79, but we're going to round that to 1.80, and we're going to get a value of 1 here. Now, that being said, these are decimal numbers. We actually want a whole number. So we need to come up with a strategy for finding a whole number. There are different ways to do this, but this is how I approach this. I can rewrite 2.80 as 280 divided by 100. 1.8 becomes 180 divided by 100, and 1.00 becomes 100 divided by 100. Now, one of the biggest mistakes that students tend to make is wanting to round 2.8 to 3, 1.8 to 2. Those numbers are a long way from whole numbers, so you're best not to do that. So what we're going to choose to do is now multiply the denominator by a number that allows us to get a whole number. So in this case, the hundreds cancel, which gives you a whole number ratio of 280 to 180 to 100. And now the quest becomes a quest to simplify. If we divide, you can choose to go any which way here. If we could divide each number by 10, once again, if we did that, we could divide these by 10, which would give us numbers of 28, 18, and 10. Again, it looks like we're going to have to divide these, since they're all even, by a power of, or by 2. So we'll divide these by 2 once again, trying to get the simplest whole number ratio. And the value that I come up with is 14 for carbon, 9 for hydrogen, and 5 for chlorine. So this ratio of 14 carbon atoms to 9 hydrogen atoms to 5 chlorine atoms is our simplest whole number ratio, which by definition is the empirical formula. So the empirical formula can be said, where do I want to write this? The empirical formula of carbon to hydrogen to chlorine is in fact C14H9Cl5, and that is the end result. In other words, when you use percent composition data to find the empirical formula represents the simplest whole number ratio of the atoms together in a compound. And with that, that ends the solution to this problem, and I hope you find it helpful, and it should help you to find solutions to similar types of problems that you encounter.